right, any questions before we get started? Okay, so the last thing that I gave you was this theorem 726. Suppose A is a subset of real numbers with three properties. It's closed, it's non-empty, and it's bounded. Then A contains its supremum and its infimum. So I'm going to go through a proof of this because this will kind of give us a feeling for the sort of flavor of proofs in here. I'm going to prove there's two statements about the infimum and the supremum. I'm going to prove the infimum and leave the rest to you. It's a good exercise. Let L equal the infimum A. And remember what this is. This is the greatest lower bound, and it's actually a real number. We want to prove that in fact it's in the set. Suppose L is not in A. See if we can get a contradiction out of this. Now, if L is not an A, then it's in the reals, not an A, right? And what do we know about A? A is closed, so R minus A is, if I remember what it is, complement of closed set is open. Right. Good. Hence, for some delta bigger than zero, the neighborhood about the point L is in A. Oops, not A, but R minus A. So, hence L plus delta, it's also a lower bound. Or right, because everything in this delta with everything in here is an R minus A, so L plus delta is also a lower bound, right? So it's a slightly bigger lower bound, and this is a contradiction. But L plus delta is bigger than L, and this contradicts fact that L is indeed thing. And like I said, proof for it's being it contains supremum is similar. Here is a corollary that we're going to need. A is a closed set. In the reals, suppose X is an element of R. If A intersect if this is not empty, for all positive delta, we're going to use this as a tool later. So here's what we're saying. Let me kind of attach a pictorial meaning to this before we actually concretely prove it. So suppose you've got a closed set here, A. And X is some point in the reals. Now you've got this extra bit, and that is A intersect any neighborhood around X. As long as the neighborhood has a positive radius and it's not zero, it must overlap. So my picture can't be right, because notice the small neighborhood around X is not in A, right? Now, if the set is open, could I let X be this point? And the answer is yes, because notice, no matter how small of a neighborhood around X you get, there's some stuff from A. You agree with that? So is X in A? No, but A is not closed. If I assume that this is closed, I can't get away with this. That's what this is saying. If you have a set that's closed, and there's a point that no matter how small the neighborhood, you get around that point, it overlaps with A, then that thing already had to be in the closed set in the first place. So let's now that I've kind of got a picture in my head, let's see if we can prove this. If X is not in A, then X U is no set. Right. So if X is not in A, then X is in the complement of A, which is an open set. And what does it mean for the set to be open? That means that there's a small enough neighborhood around X such that it's completely contained in U. Since U is open, there exists delta bigger than 0, such that, and let me remind you, there's a neighborhood around here that's completely within U, right? Hence, the neighborhood X delta intersect A is the empty set. But that contradicts our assumption. So X must be in A. Any questions on it? Okay. I talked to you all a little bit about compact last time, right? I think of parking spaces, right? Compact, they're always small. It's compact in a certain sense, it's a notion of smallness. The definition that I'm going to give you from this might seem a little strange. I'm going to give you a spoiler here on the real line, what it means to be a compact set. And we're going to prove this eventually, is the set is closed and bounded. Right? Keep that as a picture in the back of your mind. I'm going to give you this definition here. Compact 728. Let A be a subset of reals. And this can be done again more general in more general settings, reals. A collection C a collection script C of subsets of R is a cover for A if what is a cover? it just makes me think of which blankets, and that's exactly what it is, and all this is. If A is covered up by all the blankets in my cover, then that's what we call it. So a cover of a set is just a bunch of sets, and when you union them, it contains your original set name. So it covers and the kind of covers we'll be looking at most if each C and C is open, we call C, and open cover. Right? And finally, if fancy D if B is a subcollective, maybe I don't need all the blankets, maybe I just need some of them, such that A is contained in then fancy B is a subcollective. Uh, so, with that, okay, so what is a cover? It's just a collection of sets. The cover. Can somebody give me a cover of all the reels? I've got a smart aleck answer for this. Here's a cover for the reels. The reels, right? Just a giant blanket over it. There you go, right? I'll give you one that's a little more interesting. So let's see people. Smart aleck. I'm gonna do all my covers as open covers. Notice these are open sets, real open set. Notice one blanket here is all that's needed. Here I needed countably many blankets. Here's a big cover. This is every stinking interval. I've used every one of them, right? This is an uncountable cover.
So how is the first one, if it's just like the naturals, like, if it's just natural numbers, how is it like same, or like, how is that?
Any number is in between two natural numbers, right?
Oh,
Oh, actually, you know what? She's right. This isn't a cover. Anybody know why?
it's an exploration.
Thank you. Gosh, you guys are all open. Good. How can I fix this? That doesn't do it either. Good heavens, I'm seeing double. So, that doesn't do it either. There's a problem with my cover here. Can somebody name can somebody name something in the reals that's not covered by my cover? What's that now? No, I've got all the irrationals. Anybody give me a single number that's not covered? What's that?
Zero? Oh.
No, you're right. Zero's not ever in here. Because we've got the interval from 0 to 1, we've got -1 to 0, but we never cover up 0, do we? In fact, we never cover any natural number. That's what a big cheater I am. That'll do it. Because now they're overlapping and I'll get everything. Given any number, you can, and I'm glad that you asked that question, Sophia, because I said, what did I say? I said between any, well, at first, of course, I thought I had said Z, but I said between any number can be put between two natural numbers, but that's not true because the natural numbers themselves are not covered in this, right? But now with this overlap, now I get every natural number and I get every, yes.
If you had not made it open, could you have done?
No, and he's right about that. I want my covers to be open, but yeah, if I had done square bracket in +1, that would also be a cover. It wouldn't be an open cover, but it would be a cover. Yes.
For n, like +1, why doesn't that work if like you had like n equals -1? Like, then you have -1 and 0.
But you don't have the
Oh.
endpoints. Yeah, so you're missing all the endpoints. That's the problem. That's why I made it overlap, because that'll put all the midpoints in the middle of some interval. Everybody okay with that? Okay, how about this? Somebody give me a cover for this. How about this? Let me do this one first. Let me come back to this. Um, Actually, right. Actually, let's do this. Let's do this. Minus one. That. Let's do what I want. Half, minus half. So what do the symbols look like? So I claim this is, the first one of these is minus half, 1/2. The next one is minus 2/3, 2/3. The next one is minus 3/4, 3/4, minus 4/5, 4/5, etc. It continues the process. So you go out length 1, length 4/3, length 1.5, and so forth and so on, right? You get bigger and bigger. Would everybody agree that this is an open cover for this? Because notice, no matter how close you are to 1 minus a very small amount, you're eventually going to exceed that with this fraction, right? Because the limit, this is basically n over n plus one, right? And that goes to one, as n goes to infinity. Do I agree? So for large enough n, you're gonna get everything you need. You don't need the one, because it's an endpoint, so you never get to one, but that's okay. Do I agree with you? How many blankets do we need here? Infinitely many, right? Can we use only finitely many of these, to take care of business? We can't, can we? Right, we have to use infinitely many. Okay. Do the same thing, minus 1, 1. I want you to give me an open cover of that needs all the blankets. It's easy enough to do here, wasn't it? Half, 2/3, just kind of grow out. Can you do it here? Well, will this original one work? What's wrong with the original cover?
It never actually reaches -1 or 1.
And you need that, right? This thing's getting cold at night, right? Its toes and fingers are sticking out of the blankets, right? You didn't ever pick those up. Right? Well, so let's throw in, look, I do. Here's the way I'm gonna do it. I'm gonna do the same thing I did last time. I'm gonna do this forever. But then at the end, I'm also gonna throw in this. Let's say, I need to make sure it's not cold at the end. We'll say 9/10, or well, let's say 0.9 to 1.1 union, gotta get the toes to, minus 1.1 minus 0.9. So I'm gonna throw on those two last orange blankets to cover up the fingers and the toes, right? Do I need all the blankets? Now I don't need all the blankets. Why? Right, look what happened here. What did I do with this interval here? Here's my first, here's zeros in the middle. Here's my first blanket, then my second, my third, and so forth, and so on. And I kept throwing the blankets out here. I didn't quite get the fingers and the toes, so I threw in these blankets here. Now I only need finitely many, right? Because once the blankets get inside of these neighborhoods, I can throw all the rest of them out. This is what it is. Definition. A set C and R if open cover of K has a finite subcover. That is to say, if I pick any collection of blankets, any arbitrary collection of blankets, and I cover up the interval, if I look back at it, I'll say, you know what? I only needed this finite number of blankets to do it. That's all I need. This is an example. The reals is not compact. Certainly, this has a finite subcover, but it has to be for any cover. This one here does not have a finite subcover. This one also does not. All right. The original with the open intervals here, this was a cover of the interval from -1 to 1, not including the endpoints. that had no finite subcover. Couldn't do it. Notice though, this one here, when I threw in those extra ones, you have to have a finite subcover. Now, this is not a proof that this is compact. Because after all, this is just an example. How do you know, Jim, that you're just not being clever enough? You could have done some other kind of weirdo, infinite collection of blankets that you can't pull it down to finitely many. But that's what we can prove, that a set that is closed and bounded is compact and vice versa. Any questions on that? Able to do this. So this is kind of the first big theorem. This is actually behind the scenes in your calculus classes and stuff. This is part of a big engine that probably wasn't really even discussed in the calculus class, but it makes a lot of things work. Theorem. Heine-Borel theorem. Or it's compact. Actually, I'm gonna put this more in. If and only if C is closed and bounded. This is a huge theorem. Not just on the real line, but in the plane, in space, in n-dimensional space, set is compact. That is, every collection of blankets has a finite subcollection, if and only if it's closed and bounded set. So we only consider n equals 1 is actually the important case, and I'm just going to focus on that here. So I'm going to look at a subset of the real line. I'm not going to worry about the plane or anything like that. So one direction is actually fairly straightforward. We want to show the compactness implies both closed and bounded. And what I'm going to do is I'm going to suppose that your set is not bounded and show it can't be compact. And then I'm going to assume it's not closed and show it can't be compact. And then I'll have gotten that direction, right? Suppose first that C is not bounded. And I'm going to use this little factor or this assumption about C to give you an open cover that has no finite subcover. It's for all in the natural numbers, there exists an element not constant, yeah. Right. Because what it means to be bounded is there is a real number that is both, there is a real number that is a lower bound and a real number that is an upper bound of the set, right? If it's not bounded, no matter how wide this interval about 0 is, there's something still outside of it that's in C, right? No matter how I try to put it inside an interval, there's always something outside of it. Right? Good. Now consider It's an open cover of R. Right? I mean, everything in the reals is in the interval from n to minus n for a big enough n. Pick any real number, take the greatest integer function and add one to it, it'll be in that interval. Right? So is an open cover of C. Because if it covers all of R, it certainly covers C, which is a subset of R. But there exists no finite subcover. If so, there exists M in the natural numbers such that well, if so, then our cover M1 minus M1 if so, I can put C in that finite list. I can also assume that M1 less than M2 less than MK. And note, X sub MK is not in U of MI minus MI. Because it's outside even the biggest interval. Okay, so if the set is not bounded, then I'm explicitly giving you an open cover that cannot possibly have a finite subcover. On the also now suppose C is not closed. So we see if it's not bounded, it can't be compact. Let's see what happens if it's not closed. Then U is open. And now we're going to use some of the properties of open to give you a problem here. Oh, I'm sorry, right. But I'll try. Since C is not closed, then its complement is not open. There we go, that's better. So what does that mean? What it means to be open is every point is an interior, right? That means every point has a little neighborhood around it, so on the set. So if U is not open, then there must be a point that is not interior. There exists U such that U is not interior. So for all delta bigger than 0, any neighborhood of U contains some stuff that's not in U. So any neighborhood about this little point U has to contain stuff that's not in U. But if it's not in U, it's in C. So for all delta bigger than 0, there exists a point in this neighborhood and also C. So in other words, this is not the empty set, right? Now consider closed interval from u minus one to u plus one. So now, this is the neighborhood. So here we pick delta equals one, but we're also closing it up, right? So this is the neighborhood of with one with the endpoints added here. Note first that there are infinitely many points in C. In the neighborhood from u to u plus one. Without loss of generality. Anybody explain that statement? to me? So let me kind of justify that a little bit. Here's u plus one, here's u minus one. Right? Now, no matter how small I make this, there's a point here in C. Right? That's what we said, because every neighborhood has intersection C, right? Okay, so I'll make this a little bit smaller. There's still one in C. And I'll make it a little bit smaller. There's still one in C. And so I can continue this process. Yeah, and that's why there's infinitely many. Now, I did claim there's infinitely many on this side, right? That's the without loss of generality statement, right? Because it's conceivable that there's infinitely many on this side and only finitely many on this side, right? But one of the two sides has to have infinitely many, right? Because if there's only finitely many orange points on both sides, then there's only finitely many. Agree? And so one of the two sides has to have infinitely many between u and u plus one, or well, or you could go from u minus one to u. And I will say without loss of generality that at least this side has infinitely many points from C. Everybody okay with that? Okay. All right. So now we build an open cover for C as follows. Start with, I'm gonna let V equal R minus the interval from u minus one to u plus one. That's one big open section, right? I mean, basically, I've taken this little small interval of length 2, and now just my first open set is everything else on the real line. So this allows me just now to concentrate on this. My next one is W equals u minus 2 to u. Let me point out before I get too deep in the weeds here, that these are both open sets, right? Because this is closed, so V is the complement of closed set. So this is open, right? And this is open because I got the round brackets here. Notice I started to the left side of u minus 1, and then I go overlapping to u, right? So now basically, what's left over once I've jerked this out is basically the what's left over in this is just the interval from u to u plus 1. which has the infinitely many points in it, see. So. Now, here's where it gets kind of funny. If there exists a point. C1 that lives in, C, intersect U plus one. But not in U 1/2. So here's what we've got over, might help draw a picture of this. So if, let's see, so what are we left with after we fill this off? We're left with the interval from U to U plus one. Now, if it turns out that we can find a point, say C1, that's in this interval, but not in the interval from here to here. So if there's a point up here, then I'm gonna let U1 be time the neighborhood about C1 1. So notice that this thing is to the right of 1/2, so I'm gonna have a interval of 1/2 about it, something like that. And then we're gonna kind of fill this around. If there's no point from C1 in this range, I'm gonna just let U1 be empty. And I'm gonna move on then to U2. Now, if there exists C2 in C intersect U plus 1/2, but not in U to U plus 4. So now we look, so we looked in the last half, then I'm gonna look in the last half of what's left over, right? So now I'm hunting from, I'm hunting for not up to a fourth, but between a fourth and a half. If there's a C2 here, then I will let U2 equal the neighborhood of 1/4 around C2. And U2 empty otherwise. Or generally, so the general formula for this. I'm gonna let, if Cn is in, C, intersect, U 1/2 to the n minus 1. That makes an A for it. Yeah. This is in, right, intersect U 1/2 to the n minus 1, that's right. Minus U 1/2 again. Then UN is equal to neighborhood about Cn, 1/2 to the n, radius. Or UN is the empty set if no such. C. Notice that this one, since the interval from u plus 1 contains infinitely many elements of C, this is an infinite cover. That has no finite. So an infinite cover of C, I should say. Notice that the first set gets everything except this, then we're down to the interval from u to u plus 1. And what do? We cover something in the second half by something of with this. This may pick up a whole bunch of other points, but it doesn't matter. Because once I pull this out, there's infinitely many more in here. I'll look for things in this half. And I cover it by length of, well, radius 1/4, width 1/2, I guess. Covered by that. What's left over, there's infinitely many left over. I cut it by radius 1/8 and so forth and so on. There's no way to extract the finite subcover. Because if you only use finitely many, you're going to be left with this, with some small amount of this left over. And so infinitely many points left out. Everybody kind of okay with that? Yes.
Before the generally, is it u u plus 1/2 over?
Yes, I really should have written, yeah, it should be, where did I leave this? Yeah, this should be, thank you, plus 1 over. And that one, and this should be, u plus 1 over. That's good. Yes, thank you. Okay, any other questions on this? Now, suppose the C is closed and bounded and C is an open cover. We have to show that it emits a finite subcover. Let me talk about it. Let me just set this up. We're not going to be able to finish this today. So the other direction. So the conclusion that we've come to so far is, so if C is compact, then C is closed. So if you can find a set that's compact, so it's got this property that if you cover it up by any collection of open blankets, then there had to be finite many to do it. If you're compact, you have to be closed and bounded. Now, what we need to do is we need to show the converse. So, okay, so here we're going to define some sets to get us started off. So we'll hit this next time, but suppose C is closed and bounded. And suppose that strip C is an open cover. need to show the, see if it's a finite cover. Okay, so this is probably a good thing to leave you to think about for next time. I'm gonna define the following two sets. So it's probably good to think about this before next time, kind of record so we know what this is. Firstly, for all X and R, we define CX. This is gonna be the set of A and C such that A is less than or equal to X. So given the set C, which is closed and bounded, CX is gonna be everything in C that's to the left of whatever the subscript X is, right? So C1, everything in C that's to the left of one, including one. C1/2, everything is to the left of 1/2, including 1/2. And D, this is the set of all real numbers X such that CX is covered by finitely many elements of the cover C. Okay, I'm gonna use these two, doing the correction. That's enough for now. Any questions on this? All right, well, I will see you folks on Wednesday.